Hi everyone, welcome to my video here. This is my project that I set out to start so that I could try teaching people what I think I know or what I know. Really, it's a way that I can truly test what I know and figure out what I think I know versus what I actually know. And by doing this, I hope that there are people who can actually benefit, and I'm hoping that if there's something I say that's wrong, maybe you can catch me on that. I'm doing this specifically because I learn by doing, and I can't find anyone who will sit long enough to listen to me talk about vector spaces and, eigenvectors and eigenspaces and, all that. So I'm hoping I can reach to people online who are willing to learn with me. As I go through linear algebra. This is not my first time taking the linear algebra course. And that being said, I've been studying it for like a year and a half now, I guess. So I'm not a stranger to it, but this is still something that I really want to use, that knowledge. So I'm hoping this is the right platform, if that made sense. So if you have any feedback for me or anything you'd like to tell me, you can let me know on the mail over here, failandlearn@gmail.com. And with that being said, we can begin. So when I started studying linear algebra, my class in university, we learned about subspaces first. And then the second section, we started studying vector spaces, and this all kind of confused me because I was like, what is the difference? And I don't think they really highlighted that at the beginning and just brushed over the fact that there's something called vector spaces. And, with me surfing on the internet, I also found something called subsets. Well, actually, I really knew that, but, it didn't. Anyways, so it was just this whole messy thought of what is the difference between a vector space and a subspace and a subset. What are they? Fight, maybe, I don't know, it's like they're battling in my head, and this is kind of how I felt. Anyways, so we'll start with a vector space, what it means, because now that I think I figured this all out, a vector space is basically a space whose elements are vectors. No duh. And it's defined by two operations. Vector addition, oops, wrong color, but whatever, I don't want to rewrite this. And scalar multiplication. So these two operations must satisfy certain 8 axioms or properties, but axioms is a cooler word to use instead. But before I go on there, I'd like to specify this points on A and B. Okay, change colors. So let's start with A. Change the size, it's so huge. So for vector addition, let the vector space be called V. And as I said earlier, the elements of a vector space are vectors. So let there be a vector X and a vector Y, both of which are in V. So what A is saying is that if I have X plus Y, that should also be in V. And that's all it says. And then B is saying that let there be, for example, a vector X that is in V. And there is some scalar number C that's a real number, basically. And if I do C times X, that should still be in V. So that's what these 2 points are. these two that define a vector space. And I can give you examples of vector spaces, but I'd like to go over the 8 axioms first. So because in addition to those 2 points, the vector addition and scalar multiplication, these 8 properties or axioms, use that word because it sounds better, hold. The first axiom is that let there be an x, y, z. These are all vectors living in vector space V. And if you have x plus y plus z, that should be equal to. It's the same as doing x plus y plus z. Alright? And I think this is called associativity or associative property or something like that. And another axiom is that if you have an x and y that is in V, and you have x plus y, that should be the same as y plus x. I think this is commutativity. Okay. The third one says that there is a zero vector. There is a zero vector such that x that is in V, such that if you have this x in V and you do x plus 0, the zero vector, you get, well, what do you know? Shocker, x. I don't know why we have to go through these simple definitions, but I think it's useful because sometimes we start thinking about vectors in terms of real numbers, and I think ignore what I just said. I really think it's just that they want us to know that these are the properties, and not to just assume that they are going to be just like real numbers, but, going through them now, no, it's not blue, whatever. The fourth one, so let there be this x in V. If there's this x in V, that means there has to exist this negative x such that x plus this negative x is equal to 0. And I'm just stating these right now, but I will go through an example that I've tried with one of the vector spaces to show you. So the fifth one, if x, y, and y are in V, and there is a scalar c, it's a real number, then cx plus y equals to c of x, c of y. This is what distributivity, or I can't pronounce these words. 6. So there's this x in V, in the vector space V, and there's these two scalars that are real numbers. That's what the symbol means, real numbers. Then c plus d equals to c of cx plus dx. All right. 7. For some x from vector in V, and c the scalars that are real numbers, then CDX is CDX. Pretty sure you knew that already, but this has to be defined just cause I don't know why, but they do it. And finally, if there's a vector x, there's some vector x in V, then 1 times this vector x is equal to x. Okay? So these are the 8 axioms a vector space has to have in order to be a vector space, in addition to the 2 properties of addition and scalar multiplication. So what are vector spaces? Well, examples of vector spaces is like Rn, or the set of all these functions, the set of all polynomials. These are examples of vector spaces. Oh, and there's also the set of continuous functions. It's like a subset of a set of all functions. It's with the condition of them being continuous. Because there were some functions where they would be like that, and they would continue from somewhere else, and that's not continuous. So these are examples of a vector space, from vector spaces. I can go through the 8 axioms with you right now for Rn, just to show you. This is the one I worked on. Again, if there is anything iffy about it, just let me know. I'm pretty sure I did it correctly, but I can't beat my own marker. So let me find an example where I wrote my. So let's start with the number 1. For x and y and z in V, and V in this case is Rn. I'm just gonna write that here so you know. We're gonna see if x plus y plus z is equal to x plus y plus z. Okay? I'm gonna let x equal to x1, because it's up until it's in Rn, so it has to go from x1 to xn. y1 to yn, and z1, z1 to zn, zn. This is the end of the story. So that wasn't even funny. Why am I laughing? So let's see. If I have, I should probably state that x1 all the way to xn, as well as y1 all to yn, and z1 all the way to zn are all real numbers. Just remember, if that might sound a bit weird if you're not thinking right now, but like, for example, if I had some vector x in R that lives in R2, and it would be 1, 0, like this is an example of them. And if you look at the entries, they're all real numbers. I thought I would state that because sometimes when you're not paying attention, you're like, what? I'm trying to make things easier for people. State the obvious. So these are real numbers. If I have x plus y, that would be x1 plus y1 all the way xn plus yn. Remember, if you are adding two vectors, you add them entry-wise. So like assume I'm adding a vector a0 and 0b. That would be a plus 0, 0 plus b, or a plus b. In this course, you'll see that we do a lot of simple steps. I'm just doing it because they did it. Maybe it'll help you if you're still confused about things. All right, so just knowing that this is how you would add vectors, coordinate-wise or entry-wise, I'm doing the same thing to the x plus y with their x1, y1s. Okay. I'm just gonna group them all together. And if I wanted to add the z to this, x, y1, x plus y1 plus the z1, z end. This would still have to go coordinate-wise. So the first one and the last one together. So that would still be x1 plus y1 plus z1 all the way. If you're noticing, I've been saying z and z. I never knew there was a difference between American and Canadian until people brought it up, but I've been saying either one freely. Because of TV, I guess. So if it bothers you, I'm sorry. I'm not sorry. That's how I am. Okay, back to axioms. All right, so this is what we have. Since these are scalars or real numbers, we know that if you have 2 plus 3 equals to 5, it doesn't matter if you switch them around. It still equals to 5. So I can switch these up around to have it, wait, let me think right now. My mind's kind of jumping ahead sometimes, so I think I saved that explanation for another axiom. Let me just check my notes. Yeah, okay. 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 Well, if we had like 2 plus 3 plus, another number that's easy to deal with, it wouldn't matter if I added these first or if I added 3 plus 5 these first. Answer's still the same. So I can group this because these are real numbers and they have properties of real numbers, I assume. So I can group them to have it as x1 plus, not x1 plus, but like x1 all the way to xn, adding to y1 plus z1 all the way to yn. And that would be the same as saying x plus y plus z. Alright? I don't know if I want to go through all of the axioms. I don't know if you need me to go through them because they are kind of very simplistic in idea. So I think I'll just move on because I'm getting bored of this. There are all 8 of them, and one just took me that long. If you really want me to go through all, I will, but I don't think anybody really wants me to. That's what a vector space is, and I gave you examples of the types of vector spaces. The real question comes in. So what is a subspace? Or maybe you're asking what's a subset. Well, vector set. The vector space is basically a set, right? And when you have a set within a set, it's a subset, all right? But being a subset does not necessarily mean you are a subspace, or a vector space is just a set within a set. Okay? So what is a subspace? Or a subspace is basically a vector set within a vector set. So for example, R2 is a set contained in Rn, right? And R2 is a subspace. It's a subspace. It's also, I think I should formally write out the definition. Maybe it'll be clearer for you. I want my blue background first. I know it's blue putting you to sleep. Black, do it. Oh, black. Okay, let's try black. White. Where's my white? There we go. Oh, that's cool. Okay. I'm gonna write the definition so that you know. But basically, let V be a vector space, and it has the operations with scalar and scalar addition, vector addition, scalar multiplication, and W let W be a subset of V. Okay. So W, for notations, is contained in V. Then W is a subspace of V if and only if the following conditions hold. And the first is that W contains the zero vector. Second one, so if there is an X and a Y in W, X plus Y should still be in W. And the term for that is closed under vector addition. No, it's not black anymore. I hate black. And the last one is that if there is some X in W and there's a real number, scalar, that's a real number, then Cx should still be in W. And if all these three conditions are satisfied, we can say W is a subspace of V. Okay? And that's actually, I should have mentioned, that's a theorem. Oops. There's also a definition that goes with it. So V is a vector space, and W is contained in V as a subset of V with respect to the vectors of operation in V, in the vector space V. Then W is a subspace. W is a subspace. Wait, I should. Oh, wait, go back. I'm probably jumping something right now. I'll go back a bit. So if V is a vector space and W is contained in V, and the operations that go along with the vector space V, and I think W is also a vector space, then W is a subspace. What this means for us is that given that you're given something like W containing a known vector space V, and you're asked to find if it's a vector space or not, it's much more easier to test if W is a subspace than it is to test, well, for me at least, the whole I'd rather test for three conditions than 8 whole axioms. It's probably faster that way, but the condition is that V, since W has to be contained in a vector space, so therefore a subspace is a vector space within a vector space. It's a smaller vector space, basically. Other examples include R2, because that's in Rn, I believe. And the set of all continuous functions lives in the set of all functions. And I think it's also a subspace or a vector space, and you can always check for yourselves. And I think, let me see if I have another one example. I think that was it for my examples with subspaces, and that's it for what I have for this video. I hope that clears things up for people. I did really kind of talk too much, but this is my first time making a video like this, so forgive me until I can actually get the hang of things. I hope I can upload another video, one on the other, building up on linear algebra stuff. Please leave me feedback, questions and stuff. I really don't want to make videos that suck. I want them to be actually informative, and benefit for you and me, for me to actually learn and perfect, or not really perfect, perfection is, crazy. 99% get, okay, at least get 99% of what I'm talking about, or what I'm learning, and actually use it and help others. And I really hope that you on the other end can understand, and things might be clear, because I understand things are confusing. If not, I hope I did not, the very least, I hope I didn't confuse you, and it was somewhat interesting to watch. If not, I know it might, I do drag on and on and on like I am right now. I hope it wasn't boring. Just leave me suggestions, please. Thank you. Bye.